Okay, notes 8, the geometric distribution. So the geometric probability distribution, there are 4 requirements for a setting to follow the geometric probability distribution. And these 4 items include the 3 requirements for the Bernoulli trial or the binomial probability distribution. So you'll be able to see those 3 similarities and then see what makes the geometric one unique. So the first one is that they need to have 2 possible outcomes that we label as success and failure. The next one is it has to have a fixed probability, so the probability of success is labeled P. And then it has to have independent trials where we can use the 10% condition to assume independence. So all these things are similar to what we just talked about in the binomial distribution. What makes this one unique is that the next one is called first success. So instead of having a fixed number of trials, we're going to continue to do these trials until we reach a success. Once we reach a success, then we stop. So that may take 1 trial, 20 trials, 100 trials, how many trials it's going to take us to get a success. So what this means is that what we're looking for is the first success that will occur. We do not have a fixed number of trials, okay? Which means we keep going until we hit that first success. So for example, if X is equal to the number of trials until you reach the first success, okay. If we look at each of these examples, so for example, number 1, how many times do you have to flip a coin before you get a tails? So let's say I have everyone flip a coin, okay? Maybe your neighbor to your right does it on the first try, okay? So that means they only had 1 trial before they reached their first success. But let's say the person on the left took 20 times before they got tails. So that means they had 20 trials before their first success. Before we look at the formula, let's see how we get it. So in this example, it says you roll a 6-sided dice. Let X equal the number of trials until you roll a 6. So we did something similar in class. So it says, what is the probability that you roll a 6 on the first trial? So this is the same as saying the probability that X equals 1 is going to be 1/6. Okay, then it says, what is the probability that you roll another number the first trial, but 6 on the second trial? Well, that's the probability that if we get our success on the second trial, that means we had a failure the first trial, and then a success the last trial, which means we get 5/36. Okay. Then it says, what is the probability that you roll another number on the first 2 trials, but a 6 on the third trial? So this is the probability of getting a success on our third trial, which means we had 2 failures, then a success. Okay? You would continue multiplying all these together. Lastly, it's saying, okay, let's say you roll any other number on the first 3 trials, but you get a 6 on the 4th trial. Well, we have the probability that X is equal to 4, so we get a success on 4, is equal to a failure times a failure times a failure times a success. So all those numbers together will give you the probability that you will get a 6 on the 4th trial. So it says, using the 4 outcomes above, create a table showing the probability distribution. So when X was 1, we had 1/6. When X was 2, we had 5/6 times 1/6. When X was 3, we had 5/6 times 5/6 times 1/6. And then when X was 4, we had 5/6 3 times, and then 1/6. So our failures, then our success. So it says, can X be 0, Y or Y not? So X cannot be 0 because you have to have at least 1 trial to find the success. So X cannot equal 0 since we need At least one trial. When do we stop the table? In theory, we never stop. We're going to go on forever without getting a success. Okay, so in theory, never. What probability pattern are you noticing? So it looks like we have the failure probability, so that 5 to the 6, to the power of the number of failures times the probability of success. Okay, so really what we just found was the formula. The formula of the probability of x equals x is equal to the failure, 1 minus p, to the number of failures, so x minus 1, times our success, which means our mean, mu of x, is equal to 1 over p, and our standard deviation is equal to the square root of 1 minus p over p. Okay, so let's look at some examples. And these examples, they're going to want us to do this by hand and then make the interpretation. But what I'm going to do is I'm going to set up the problem, give you the answer, and then when we look at the calculator stuff, you'll see where we're getting the answers from Desmos. So it's going to give us a scenario just like in the last notes, and then we're going to have to explain each of the following. So the first scenario says you toss a coin until you get a tail. So x is going to be the number of trials until tails. We have two possible outcomes. We can get tails or heads. There's a fixed probability, and that is p is equal to 0.5, or a 50-50 chance. And we know this is independent because if you flip one coin, it's not going to impact your results for the next time you flip a coin. And then we know we got a success when we flip a tails. Okay, so it says find and interpret the probability of x equals 4. So the probability of x equals 4 is going to be equal to the probability of failure, so 1 minus 0.5, to the number of trials, 4 minus 1, times the probability of success, 0.5. Okay, when we solve that out, we get 0.0625, or in other words, the probability that you get the first tail on the fourth flip is 0.0625, or about 6.25%. Number 2 says a company reports that 75% of emails it receives is spam. So x is going to be the number of trials until we get a spam. We have two possible outcomes, and that is spam or not spam. We have a fixed probability given as p equals 0.75. We know that these are independent trials because we're assuming you have many emails in your inbox. So yes, it's an independent trial. And then we know we have a success once we open an email that is spam. So we open emails until we get spam. So it's saying, let's say our probability is x equals 2. Well, that's us saying, okay, what's the probability that on the second try we open a spam? So this is equal to the probability of failure, 1 minus 0.75, to the power of 2 minus 1, the number of times we're doing that trial, times the probability of success, which is 0.75. This gives us 0.1875, or in other words, the probability your first spam email is the second email you open is about 0.1875 probability, or about 18.75% chance. Okay, number 3 says type A blood is found in 43% of its population. X represents the number of trials until type A. So that means until we get a type A blood type that is found. We have two possible outcomes. We either have people that have type A or not type A. The probability is given to us as P is equal to 0.43. Our trials are independent because we're making the assumption that there is many students in our population. And we know we have a first success if we check students until type A blood is found. So it says find and interpret the probability that X is equal to 5. Well, the probability that X is equal to 5 is equal to the probability of failure, so 1 minus 0.43, to the power of the number of trials, so 5 minus 1, times the probability of success, which is 0.43. So this gives us 0.045, or in other words, the probability that you don't have a student with type A blood until your 5th student is about 0.045, or about 4.5% chance. So the next part here talks about geometrics on the calculator, just like it talked about binomials on the calculator. I'm going to go ahead and skip this part, because we already filled this out on the binomial notes. So what I want you to do is I want you to fill this out using the binomial notes. Okay, it's going to be exactly the same. Okay, now we're going to look on how to do this on Desmos. So looking at number 4, it says type A blood is found in 43% of the population. What is the probability that you will not find a person with type A blood until the 3rd student walks in? So here we can identify our probability P. P is equal to 0.43. We can also identify that X is equal to 3 because it's saying we're not going to get someone who has type A blood until the 3rd person. So this is the same as saying the probability that X is equal to 3 is, and then we have to find that value. Well, our steps for Desmos, you're going to notice, is going to be almost exactly like the steps for the binomial distribution. So our first step is to click on the plus sign, and then from the plus sign, you're going to click on inference. Then you're going to click on probability distribution, and then click on geometric. Geometric only asks you for the probability of success. So you're going to type in P equals, and then in our case, that's 0.43. Okay. Then you're going to click on the drop down that is cumulative probability. Okay. And since it wants X is equal to 3, you're going to see something like the probability of blank less than or equal to X less than or equal to blank. And that is where you're going to put in 3. So to show you how this works, I'm going to go ahead and open up Desmos. Okay, I'm going to cross off binomial distribution, and now I'm following these steps for geometric. So I'm going to hit the plus sign, go to inference, click on probability distribution, do the drop down and click on geometric, type in my probability of success, which is 0.43, create distribution. From here, I'm going to click on the cumulative probability, and then within there, I'm going to type in 3 since I want to find the probability that X equals 3. And here I find the answer is 0.14. So I'm going to do the same thing for 5 and 6. It says type A blood is found in 43% of the population. What is the probability that you find the first person with type A blood within 5 students? So within 5 students, that's the same as saying the probability of X less than or equal to 5. So I'm going to go look at the regions, find the one that is less than or equal to, and switch out my number for 5, and I get my probability is 0.94. Okay. I'm going to cross off that bit of information because we don't need to deal with the complement here because Desmos is awesome and it does both less than and greater than. Number 6 says type A blood is found in 43% of the population. What is the probability that it will take more than 3 people before you find a person with type A blood? So since it says more than 3, that means we're not including the number 3. So this is the probability that x is greater than or equal to 4. So going to the regions, I'm going to pick the right region because that has greater than or equal to. Type in my number 4, and I get my probability is 0.185.